Alright, so continuing on with the p squared q, I had mentioned that the problem broke down into a few interesting cases. I thought maybe it'd be useful to actually just do two specific special ones that illustrate this idea. I picked 18 and 20 because the book also has a section on tables of groups of small order, and 18 and 20 are two of their examples, so we're going to verify the book's results in these two cases. And so let's focus on 18 first. So this factors as 2 times 9, so 2 times 3 squared, so it's p times q squared, I guess I'd say. And so, of course, the point is that there's a CELO 2 subgroup, P, and a CELO 2 subgroup Q. CELO 3 subgroup Q. Notice that Q has order 9. And so the point is that there's supposed to be two possible cases. Either P is normal in G, or Q is normal in G. To remind ourselves what happens, let's go ahead and look at what the congruence relations were supposed to be. N2 has to be congruent to 1 mod 2, and it has to be a divisor of 3. So it's either 1 or 3. Or 9. It has to be a divisor of 9, right? On the other hand, N3 has to be congruent to 1 mod 3, and N3 has to divide 2. We see N3 has to be 1. That's exactly this case. Or not this case, this case. The CELO 3 subgroup is normal in G. So as I had mentioned in the previous video, when the square prime is larger, the normal subgroup, the CELO subgroup corresponding to the square prime is the normal subgroup. And so G is isomorphic to the semi-direct product of Q with P. Why is this true? Because P and Q have coprime order, and Q is normal, so P times Q is in fact a group, and it has the same order as the whole group, and P intersect Q is the trivial subgroup. So G is the internal semi-direct product of Q and P. So classifying groups of order 18 is equivalent to classifying homomorphisms from P to the automorphism group of Q. In particular, classifying homomorphisms from some group of order 2 to the automorphism group of any group of order 9. That's all we need to classify. So, of course, there are two cases. A group of order 9 is either going to be Z3 squared, or it's going to be Z3 times Z3. So let's assume it's Z3 squared. Now what is aught Q going to be? It's going to have to be order 8. It's order 8. It's going to have a unique element of order 2. So, of course, there's two possible homomorphisms. The one is going to be the trivial homomorphism. Where the kernel of phi is all of Z2. That's going to result in the G being the direct product of Q and P. which is Z18. And then the other case is the non-trivial homomorphism that sends the generator of Z2 to the element in this automorphism group of order 2. That is its own. So our other case is that we actually have a non-trivial homomorphism here. With the trivial kernel to that unique automorphism of order 2. Note here, of course, we're identifying Q with Z mod 9. What could possibly be the non-trivial automorphism of order 2? I'm going to bet it's probably negation. Oh, yep, negation certainly has order 2. So there we have it. So we'll let P be generated by X. Q is generated by Y. This automorphism then tells us that X times Y times X inverse is Y inverse. Because that's what this automorphism is doing. It has order 2. It means when I conjugate twice, I need to get back to Y. Because negation really means inversion at the level of exponents. And so this is my automorphism. And Q has, this is order 9, this is order 2. It looks like in this case, my Q semi-direct product with P is nothing more than the dihedral group. So congratulations, when we're working with Z mod 9, we get two groups, Z18 and D18. As I mentioned before, when you're working with Z mod P squared, nothing that interesting happens. So now we're going to assume that Q is Z3 times Z3. And see if anything more exciting happens. Well, now what's the automorphism group of Z3 times Z3? Well, that's a lot more interesting, isn't it? The book points out in the section on automorphisms that when you've got the elementary abelian P group, which is what this is, then you're supposed to get the general linear group here. 2 by 2 matrices in this case, over Z mod 3Z. In other words, I'm looking at matrices whose coefficients are in Z mod 3Z with determinant non-zero. I'm going to assume that without proof for now, but I should circle back and prove that at some point in this course, because I was already implicitly using it for the Z2 times Z2 case when I was pointing out that all those semi-direct products were isomorphic. The reason why you get this kind of thing is that it's possible to, say, transpose the generator or swap the generators, which would correspond to this type of matrix. And you can do slightly weirder stuff. And so it turns out you get more automorphisms than what we're used to. And so what are you looking for? You are looking for a homomorphism from Z mod 2 into this general linear group. In other words, you want a matrix. In other words, we're looking for a matrix that is its own inverse. Oddly enough, I just wrote one down. This is order 2 in any matrix group because it corresponds to a 2-cycle in S2. It's a permutation matrix. but it's certainly not the only one if you're working in Z coefficients mod Z3, is it? So we see what we're going to want is we're going to want for a non-trivial homomorphism, we're going to want an element of order 2, which means we want a matrix whose square is the identity. It's worth pointing out that we're picking our homomorphisms up to isomorphism over here, because if two homomorphisms are equivalent, they're going to give you isomorphic semi-direct products. In particular, not only do we want this property, but if two matrices are similar, we don't want to consider them. We only want to take one, not the other. So we're going to want matrices up to similarity such that their square is the identity. And so a fact about 2 by 2 matrices is that if they're not the identity matrix, you can always prove that they are similar to one of the following form. 0 in the upper left corner, 1 in the upper right corner, and then 2 parameters down in the bottom, d and t, for unknown constants d and t. T is called the trace of a matrix, it's the sum of the diagonal entries, and d is called the determinant of the matrix. Well, yeah, it's whatever it is the determinant in this case. And so I'll leave that proof as an interesting exercise, but the point is we just need matrices of this form whose square is the identity. And so let's square this matrix and see what you get. In the upper left, you get 0 times d, you get d. In the upper right, you're going to get 0 times 1 plus 1 times t, you're going to get t. In the lower left, you're going to get d times 0 plus t times d, you're going to get td. In the lower right, you're going to get d plus t squared. And in order for these two things to be true, we see that it turns out that d must be 1, t must be 0, td must be 0, and d plus t squared must be 1. Let me be careful here. This is only in the case, this should be a negative d here. Congratulations, your matrix must be of the form where d is negative 1. And that's your only option. And the other thing I should point out, this is only in the case when A is not a scalar multiple of the identity. So it turns out if we only have one choice here, if you're not a scalar multiple of the identity, the only other case we need to worry about is if you're a scalar multiple of the identity, well then a squared is k squared times the identity, so you're looking for when k squared is 1 mod 3. Which means that k is negative 1. So our only two options are these two matrices. Oh, I should be careful. Negative 1 is plus 1. So these are our two options. And so you end up with two possible groups that are semi-direct products. And the book lists one of them as being called Z3 times Z3, semi-direct product C2, and the other one it claims is actually just S3 times Z2. So one of these choices ends up giving you S3. To get a feel, let's look at what each of these does separately. So I'm going to call this A, and I'm going to call this other one B. So let's look at the A case. So our group of order 2 is generated by X, and we're going to assume that our group Z3 cross Z3 is generated by Y and Z, And the point here is that x, y, x inverse is in fact z. That's what that matrix does. It sends one generator to the other. And xz, x inverse is y. That's what's happening in that case. In matrix, with respect to matrix B, the resulting group is just conjugating both, sending each generator to its negative. That's all it's doing there. It is very non-obvious, but if you go back, it turns out that A is similar to another matrix, A prime, which would have been -1, 0, 0. And that version of the semi-direct product would involve saying x, y, x inverse is y inverse, and x, z, x commutes with. And so here you get a copy of D6, and here you have x commutes with z, and z commutes with y. And so you end up seeing, in this case, that G is isomorphic to D6 or S3, whichever way you want to call it, and Z3. And this one ends up being this unique semi-direct product that has no other name. So we call it the semi-direct product of Z3 cross Z3 and Z2. So you start to see that when you start to work with things like p squared times q, you get a lot more complicated stuff that involves a lot more complicated automorphism groups. All right, now let's assume that you have a group of order 20. That factors is 2 squared times 5. So suppose you have a CeLO 2 subgroup, which has order 4, and a CeLO 5 subgroup, which has order 5. The number of CeLO 5 subgroups is congruent to 1 mod 5 and has to divide 4, so it has to be 1. Which means Q is normal in G. And so we've discussed this before, but when the larger prime has power 1, then that's the normal subgroup. And so G is isomorphic to the semi-direct product of Q with P for the same reason as before, because you have two subgroups with coprime order and one of them is normal. And so this is something that's going to pop up later, but whenever that happens, you have a semi-direct product. And so classifying groups of order 20 up to isomorphism is equivalent to classifying homomorphisms from a group of order 5 to the automorphism group of a group of order 4. So again, it breaks down into cases based on what P is. Do you have a cyclic group of order 4? So now we're just classifying automorphisms, or homomorphisms, from Z4 into the automorphism group of Z5, which is a group of order 4. So it looks like there's actually some automorphisms to be had here. There's obviously the trivial homomorphism, which is going to give us Z4 times Z5, so that's Z20. But then there's also the homomorphism that sends the generator to the generator. And what's one generator of Z5? Well, it's the generator in this multiplicative group. So you can check, let's see, 2, 4, 8 mod 5 is 3, 3 mod 5 is 1, 2 is a generator for ought. So let's be slightly careful. Let's say Q is generated by Y and P is generated by X. Then the generator of ought, we'll call it sigma, and it's given by taking Y and squaring it. And you can check that when you keep squaring multiple times, you get an automorphism of order 5. So there we have it. There's one of the automorphism. There's the generator of this automorphism group. And so one of the homomorphisms, the trivial one. The next possible homomorphism is the one that takes our generator x and gives us sigma. So here x times y times x inverse is y squared in the resulting group. C5 semi-direct product with respect to this homomorphism Z4. It turns out there is no nicer version for this group or description of this group. And it turns out there's more than one semi-direct product, non-trivial semi-direct product of Z5 with Z4. And so to distinguish between them, they choose not to use this name. They used to call this the Frobenius group F20. Because it has a distinguished history. And you can also generate it as a cyclic group. As 2, 3, 5, 4. And 1, 2, 3, 4, 5. So it's the group generated by these two cycles. One has order 4, one has order 5. You can check that the conjugation of this cycle by this one ends up giving you y squared. So it ends up being the same group. So that's one of the groups up to isomorphism, and it is distinct from this one, because obviously it's non-abelian. So there's two homomorphisms down. All right, so you're looking at homomorphisms to this automorphism group that has order 4. Its two generators are equivalent, are in the sense that there is an isomorphism from the automorphism group sending one generator to the other. So the homomorphism given by sending x to the other generator is going to give us the group we already considered. So the only other homomorphism you can do is the one that sends x to sigma squared, the element of order 2. Sigma squared y. It's y squared squared. It's y to the 4th. That's equivalent to negative y to the negative 1. So this is the one where x inverse is y inverse. This is the group that the book denotes by Z5, semi-direct product Z4. So oftentimes in the literature, mathematicians will use semi-direct product without the homomorphism if there's a particular special case. And it's clear to mathematicians which homomorphism is intended. And as just mentioned, sometimes there's more than one, but sometimes the other choice has another well-known notation. For instance, it's a dihedral group, in which case they wouldn't use this notation. Or it's the Frobenius group. So whenever this notation pops up, it usually means that there's one unique special homomorphism that doesn't give you a familiar group. And that's the homomorphism they're talking about. And yes, for larger groups, it turns out that they actually start to have to specify which homomorphism they mean, because you start to get into cases where there's actually more than one choice, and neither one gives a familiar group. So far we see with Z4, we get 3 different groups. All right, so now we need to take the case where we're working with Z2 times Z2. Again, we're looking for homomorphisms from Z2 times Z2 into the automorphism group of Z5. Well, now we can't send anything to the generator of order in the automorphism group because it has order 4. So we can only send the generators here to the elements of order 2. And so, of course, we always have the trivial homomorphism, which is going to give us that our group is just Z2 times Z2 times Z5, direct product. That case is never interesting. So then let's call our generators x and x prime, both order 2. And so our homomorphism is going to have to send some element of order 2 to the element of order 2 here. Let's suppose without loss of generality that it sends x to sigma squared. So this means that x inverse is equal to y inverse. We see this element x has order 2 and y has order 5. And so x and y together generate a dihedral group. Moreover, the way we set it up, x prime commutes with everybody, because v of x prime in this case, I'm assuming, is the identity. So in particular, we see that this group intersect with x prime. It's going to be the trivial subgroup. And since it commutes with everybody, we see that it's going to generate the whole group. And so G is Z2 times D10, which oddly enough is actually not on the list in the textbook. Or is it? So then this always brings up a quirk. If it's not on the list of the textbook, did the textbook make a mistake, or is this isomorphic to one of the groups in the book? Well, I mean, y has order 5, x prime has order 2. This tells you that x prime y has order 10. By similar calculation I have done previously, you can see that x times x prime y x inverse is going to give you x prime y inverse. So this is actually the dihedral group as well. So it looks like we actually got all the groups in the list. So then the question is, what happens with the remaining homomorphisms here? Because there are actually some homomorphisms left. I mean, naturally, any homomorphism is going to have to send an element of order 2 to an element of order 2, right? So the question becomes, you're guaranteed that you have to send an element of order 2 to an element of order 2. The second question is, must there be a fixed point, an element you send to the identity? If so, then every non-trivial homomorphism between Z2 times Z2 and the automorphism group of C5 must be of the form we just saw, in which case we've finished our problem. But if this doesn't happen, then there's at least one other type of homomorphism to consider. And so, of course, pick an element of order 2, suppose it's mapped to sigma squared. Now take another x prime that's not equal to x, and suppose sigma x prime is also sigma squared. Well, the one remaining non-trivial element is x plus x prime. So now if you let this be x double prime, you see we found our element. So it turns out no matter what homomorphism you work with, if it's non-trivial, it has to send one element to an element of order 2 and one other non-identity element to the identity element. In other words, there has to be a non-trivial kernel. And so no matter what we do, we are stuck in the previous case. And so we have classified all the groups of order 20. And we see that it's much easier than the groups of order 18 because we didn't have to get into the matrix groups.